Okay, we're going to talk about finding the area of these polar regions. And as you probably remember, the first time you did this in calculus, when you're first talking about integration, you had a curve as a visual, and then you inserted all of those rectangles with either the lower or the upper sums, and you shrank the length down of those rectangles to 0 as you were taking the limit of them to infinity, and that was producing the integral that allowed you to find the area under the curve. A similar tactic will be used for our polar regions. And to explain it in, I guess, the most visually simple way, I'm going to apply it just to a circle. All right. So, as we know, not all of these are a nice circle. And so we'll want to start with maybe the area of just a region of this circle, which would be a sector, right? And so let's say we want to find the area of this region of this sector between alpha and beta. And so I do want to define beta minus alpha as between 0 and 2 pi. So not more than one of the circle. So I could be a whole sector, I could be up to finding the area of the whole circle, which makes sense. We want to find the area of 2 circles. That would be silly. All right, now we'll need to know the formula for an area of a sector to make this happen. So to remind you of what that is, it is 1/2 theta, where theta is in radians, and of course r is the radius. So just like we started with a lot of little rectangles, to pull this off, we would look at a lot of little sectors inside of this region, with this being kind of like our steps or our width. So the width of that sector, I would call it the change in theta. Now that would be defined in how many sectors I want to split this up as. So delta theta would be my entire interval, beta minus alpha, divided by n. So we'd start with n sectors, and then we're going to take that to infinity to shrink it down and get the exact area. Now, if we're dealing with a circle, it's silly because we can find this area. There's no discrepancy between those little sectors and the whole thing. But keep in mind, we're going to be applying this to all of our polar shapes. And so if I was applying these sectors to, say, a petal of a rose, then I would have some of these sectors being beyond, some of them maybe matching up pretty well or being under. I'm not good at sketching this. So you're going to be putting in all these little sectors to try to approximate the area of the rose. And unlike with the curves and the rectangles where they were all kind of under the curve or all over, within a given polar graph, you would have more than likely several of them over, several of them under, you know, some combination of that happening. But our goal here is to get the sum of the n sectors of our size, oops, thinking ahead, of our size delta theta. Now, if we're taking a sum, we know then that we can write that area using summation notation. One half r squared, and for theta, I'll put in the delta theta And that will change, so sub I. But we already know we want to shrink these down. We want to take it to infinity. So we'll be applying the limit. Which we know means that we can integrate this over our boundaries. So from alpha to beta, I just pulled the 1/2 out front, r squared delta theta. And maybe a more practical way of writing this, because r will be our f of theta, we'll still need to square it, and we'll be integrating with respect to theta. Now, an important thing to note about these areas of polar curves that is different from the areas that we were finding in the rectangular plane is, like, if we integrated and found the area of this sector, it would be positive, right? And in the rectangular coordinate system, if I found an equivalent, maybe sector over here below the x-axis, this area came out negative. That is not going to happen with our polar, right? We're squaring r. We're not going to have negative answers. We're not. But where we do have problems and issues that we'll want to avoid is where we're going between positive and negative regions. And if we are going over a region more than once, right? I specified that I only wanted to find the area of this circle, not accidentally go around the circle twice. And as we go through some examples, I'll kind of point out how to avoid this, because sometimes with those polar graphs between 0 and 2 pi, you'll maybe trace it 2 or 3 times. The best way to avoid those potential issues is to just use the symmetry that we'll have at our disposal. Okay, but let me make that more clear by just getting into an example, because that's probably kind of vague right now. And to help with that, I am going to put the sketch of this. If you're not sure what it looks like, you could put it in your calculator. But I know that this is a circle with diameter 5 that is symmetric on the positive side of the x-axis. So something like that. Well, and actually, let's think of what these ordered pairs actually are. So where does a circle start? If I substitute in 0, cosine at 0 is 1, so I'd have 5. So here's the starting point, 0, 5. We start here on the graph. And let's just go at the big 90 degrees, multiples of pi over 2. Pi over 2, we're at 0. So we're here, we're rotating this way. So notice we've gone halfway around the circle at just pi over 2, not at pi. Not at pi like you'd think of on the unit circle. So that means I'll be back around at pi, won't I? Because what's cosine at pi? -1, which is -5, right? So at pi, which is here, we're going backwards to -5. That's how that happens. All right, remember how we plot those points backwards, sort of? So if we integrated this from 0 to 2 pi, we would actually be going around the circle twice, which is going to screw up our area. So I want to use the fact that when I have symmetry whenever I can with these graphs to avoid any mistakes like that. So I like to find a couple key points. Just a couple is fine, because I know I can just take that area and multiply by 2. Don't forget the 1/2 as part of our formula, right? It's 1/2 r squared theta, area of a sector. I just have to integrate from 0 and pi over 2. We're squaring our function, our radius, to get our answer. Now, since we've already discussed this one and thought ahead about what's happening at the different points, another valid way to set up this integral and get the solution would be to integrate the entire circle, which is actually just 0 to pi. So either one of those integrals will yield the answer. And please just use your calculator for these. Don't be messing with the integration. It should come out to be 19.63. I only wrote to 2 decimal places. I should have for 3, right, for the AP exam. Let me maybe do that here. So math 9. You can be in polar mode or rectangular mode, right? Because if you just change the theta to the x, it's not going to screw anything up. And let's see. So let's just maybe do the 0 to pi one. And I'm squaring that, so I'm just going to go ahead and type it in if I can get there. 25 cosine theta. See, I'm still in polar mode from the other day. So it's putting the theta in there for me. And I still have to multiply by 1/2 because I didn't type that in to begin with. So I should have a 5 there to make AP happy. It is very common to have multiple ways of writing the integral and it being correct for these. So keep that in mind. If you're comparing answers with a friend, you could have very different looking integrals, and just because their boundaries are different, it would yield the same correct answer. Okay, let's do a second one. We want to determine the area of this. It's r equals 3 times the quantity 1 minus cosine theta. And it's maybe slightly different than we looked at it the other day, but this is a cardioid. I started writing cardioid instead of cosine. So it's reflected about the axis, about the y-axis, but it looks something like this. All right, so we can use symmetry. I can find just the top half or the bottom half, whichever one's coming first, doesn't matter. So let's think at 0, where are we? Well, cosine is 1, so we're at 0, 0. I was kind of jumping ahead of myself there, wasn't I? And when cosine is pi over 2, we would be at 0, so we'd be 3 here. So that's not going to be the whole thing. At pi, we'll change our signs because of the -1, and we'll be at 6. So here we are. That means when I find this area, technically 2 and the 1/2, I don't know why I'm writing both, or I guess just to emphasize the fact that I'm doubling it and that the formula has the 1/2, but of course, for all practical purposes, don't write it. Squaring the whole radius, that whole quantity. And that will yield our answer. And I'll just write it down here for us, 42.412. All right, our last example for the day, we're going to find the area of just one petal of this rose. How many does it have? Well, it's an odd value, so there's going to be 3 petals. The sign's first petal is always in quadrant 1, so I know it's going to look like this. My petals are always a little lopsided. I know they'll be going out to a length of 4, so this would be like at now, if I want the length of 1 petal, this is where that tangents of the pole comes into play, where we're going to slice and dice. Oh, that's not a straight line. You're not going to want to find all 3 of these. Something funny could happen with your integration. So even if you wanted the area of the whole rose, you should find the area of 1 petal and then just multiply it by, well, in this case, 3. So you need to know where those tangents at the pole are occurring. And we know from our previous lesson that means setting this equal to 0 and solving. Or maybe using your calculator to make an educated guess. But I'm gonna solve it. How about that? So I know that sine is 0 at multiples of pi. So maybe write it that way. Which means my tangents at the pole are going to have it multiples at pi over 3. So where are the ones that I want? Well, I'll have one at 0 and one at pi over 3, right? That even visually looks right there. At 2 pi over 3 would be another one, etc. But really, I can use the first 2. That's going to give me that first petal. Oh, I left off my sketch. I left off this one. That's why it's it's such a bad sketch. There we go. So there's my one at 0. Oh, pi over 3. Okay. Area of 1 petal. 1/2. 0 to pi over 3. Radius squared. 4 sine 3 theta squared. Ooh, don't want to integrate that by hand. No, 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 no. 4.189 is hopefully what you'll get. Again, if you wanted the entire graph, all right, we'd multiply by 3 because this is the area of 1 petal. All right, so hopefully this isn't bad. Enjoy working with these graphs. Really getting these boundaries is going to be the most important piece to what you're doing. So good luck with that.